Hello and welcome all to this lecture series on fluid mechanics. This is lecture 3, pressure and its measurement. Okay, first of all we need to know what is pressure. Pressure, it is the force exerted by the fluid per unit surface area with which the fluid is in contact. That means if there is a fluid and that is contained in any container, means it is in contact with any surface, so the force that the fluid is exerting per unit area, per unit that surface area, that is not known as pressure. Okay, it is simply force per unit area. Okay, and fluid have a tendency to, as I have already told you, that a fluid have a tendency to flow, and whenever this movement of fluid is restricted by confining the fluid within a solid boundary, the fluid will exert forces against the boundary, and the intensity of these forces per unit area is termed as fluid pressure. That means when the fluid is contained in any container, and inside the container the motion of fluid is restricted, so the fluid will exert some forces against that boundaries. Okay, and the intensity of these forces per unit area is termed as fluid pressure. That means it is nothing but the restriction force, the restriction that is offered by the surface or by the boundary, the force, and the force per unit area is known as pressure. Okay, the direction of pressure, it is normal to the surface with which the fluid is in contact, because the fluid at rest cannot have a tangential force. Yes, because the fluid at rest cannot have a tangential force, so the direction of the force or the pressure is normal to the surface with which the fluid is in contact. Because if it is at some angle, so then it will have a tangential component, and the tangential component cannot have the fluid at rest cannot have a tangential component, so it must be normal to the surface with which the fluid is in contact, so that the tangential component is 0. Okay, this is the direction of pressure. Then we have the variation of pressure in a fluid at rest. That is also known as hydrostatic law, that how the pressure varies in a fluid which is at rest. We are please remember, we are talking just of fluid at rest at this point of time. We are not going into the fluid at motion. Okay, so hydrostatic law is also known as hydrostatic law. And what are the assumptions we are using in this? There is a static mass of fluid, there is an elementary control volume of the dimensions del x, del y and del z. As you can see in this is the control volume. We have taken this as del x, del y and del z. Okay, one side is, this is your inlet is del x, this is del y and this is del z. Okay, if there is some thing wrongly written here, so you can just correct it. This is, I think this is d dash is okay, ad is okay, and this is a dash d dash. Okay, please make a correction. This is a dash d dash, and this is cd, and this is c dash d dash. Please make a correction that this is c dash d dash and this is a dash d dash. Okay, and O is the body center. You can see that O is the body center, and the pressure at O, we have taken that the pressure at O is P, and the specific weight is omega. That specific weight is rho into G, that is omega. Okay, so if we take the gradient of the pressure or the forces along all the three Cartesian coordinate directions, that is x, y and z, so we will have that P, this side we have taken in the positive direction of x, we are taking it as minus, that is P minus del P by del x into del x by 2, because this distance from O till this face will be del x by 2, and similarly this direct distance from this O till this face, this a dash, b dash, c dash, d dash will be again del x by 2. Similarly in the cases in the x direction and the y direction and the z direction, this is P minus del P by del x into del x by 2, this is P plus del x by del x into del x by 2. Okay, and similarly if we will not please remember that we cannot equate the pressure in any direction, we have to equate the forces, and this is the, at the point O we have the weight of the component, that is the specific weight into the volume. Okay, specific weight is nothing but the weight per unit volume, so multiplied by volume we will get the weight, that is omega into del x, del y, del z. Okay, and applying the force balance along the x-axis, if we apply the force balance along the x-axis, we will get this is the pressure intensity, this is the area, minus again the pressure intensity into area, we will get 0. So on solving we get the del P by del x is equal to 0. That means the pressure does not vary along the x-axis in the fluid at rest. And please make a note that in this configuration we are taking z direction as the vertical direction, and this x and y both are the horizontal directions. And again if we do the same analysis along the y direction also, then we will get the del b by del y equal to 0. This means that the pressure does not vary along the y axis in the fluid at rest. So on combining these two equations of del p by del x equal to 0 and del b by del y equal to 0, we will see that the pressure does not vary. The pressure does not vary in the horizontal plane at the fluid at rest. And on applying the force balance along the z axis, that is the vertical axis, we will have an extra term of the weight. Extra term of the weight, we get that del p by del z is equal to minus omega, or del p by del z is equal to minus rho g. That means the pressure varies along z direction in the fluid at rest. That means the pressure varies only along the direction in which the gravity is working. Okay, in the vector notation we can write this as the grad p is equal to minus omega into k, because this direction is, or z direction is a k direction. Okay, the negative sign indicates that pressure increases in that direction in which z decreases. Okay, that means when if we are going we have a surface level and we are going up from it in that direction, the z is increasing, so that means that pressure will decrease, and in going downward from that surface plane we see that the z is decreasing. That means the pressure is increasing. That means when we are going from any surface, if we take in a datum surface and if we are going above from the datum surface, so we will the pressure intensity will increase, and if we are going below from the datum surface, the pressure intensity will increase. Please make a note of it. It is a very important concept that above the datum surface the pressure decreases, and below the pressure surface below the datum surface the pressure increases. That is very important concept. This will be used very much useful in the calculation of the pressure measurement devices of our manometers. Okay, so please make a very careful note of it that this is a very important concept. Okay, then this is all about the mathematical expressions of the hydrostatic law. So what does it says in the statement form? In the statement of hydrostatic law is like this, that the pressure in a static mass of fluid, please make a note, I am again emphasizing on this point that it is a static mass of fluid. It is a static mass of fluid. Pressure in a static mass of fluid, that means at a fluid at rest, increases in the vertically downward direction is the rate of specific weight of the fluid. This is nothing but the explanation of this, the statement of this mathematical form, that the pressure in a static mass of fluid increases in the vertically downward direction at the rate of a specific weight of the fluid. Okay, so let's move on. Then we have one term that is known as the pressure head. It is the vertical height of the free liquid surface above any point in a fluid at rest. This means that if we consider this point A, and above this is the free liquid surface, so this height h, that is known as the pressure head, and mathematically the h is given by p by omega. Okay, and some important relations for same amount of pressure. See, if we have different amounts of pressure, so from this only we can see that p is equal to omega into h. So that means p is equal to omega into h. That means if pressure is same, that is p1 is equal to p2, so we have omega 1 h1 equal to omega 2 h2. And if this is omega, if we change this omega in terms of rho and in terms of s, so we will also get the expressions in terms of s, that is the specific gravity, and rho, that is the mass density, that is s1 h1 equal to s2 h2, and rho 1 h1 equal to rho 2 h2. And these are very important relations. We will be using them very frequently, or rather I should say always we will use these expressions in the calculation of pressure using the manometric devices. Okay, so then next law comes. The first law we have seen, that is the hydrostatic law. Then next law we will see, that is known as the Pascal's law. What is that? It states that pressure at any point in a fluid, at rest has the same magnitude in all the directions. Okay, that means that the pressure at any point in a fluid at rest has the same magnitude in all the directions. It means if a certain pressure is applied to any point in a fluid at rest, then the pressure is transmitted equally in all the directions. That means that the pressure intensity, or the magnitude of the pressure intensity, is same in all the directions at a point. If you consider a control volume, and if we consider a point inside that control volume, and if any pressure is applied onto that point, so that pressure gets distributed in all the directions with equal magnitude. This is the important statement of Pascal's law, that the Pascal law said that the pressure at any point in a fluid at rest has the same magnitude in all the directions. Okay, and please do not get confused between the Pascal's law and the hydrostatic law. Pascal's law tells about the distribution of pressure, or the distribution of pressure at a point, that how the pressure distributes equally in all the directions at a point. And what does the hydrostatic law? Hydrostatic law tells you about the variation of pressure along the vertical direction, or the direction in which the gravity is working. Please carefully differentiate between these two laws and do not mix them at any cost. Okay. Then different pressures. We have different pressures. We have atmospheric pressure. We have the atmospheric pressure, and the atmospheric pressure, it is nothing but the pressure exerted by the air column. As we are living in an open atmosphere, so the pressure that is exerted upon anything in the atmosphere, upon us and upon any object, that is known as the atmospheric pressure. It has got different values, or it has got the different units. You can see that the value is 101,325 Newton per meter square. This is also the unit known as Pascal. This is also equal to 1 bar, 1.01 kilonewton per centimeter square, and this is also equal to the pressure exerted by the water column of height 10.3 meter. That means yes, and 760 mm of Hg, that is the mercury column, 14.7 psi, that is pound per square inch. Okay, and one unit is known as, also there is a unit of pressure that is known as torque. What is that? That is the pressure exerted by the 1 mm or the 1 millimeter of mercury column, which is equal to 1 by 760 of the atmospheric pressure. Then we have another pressure that is known as the absolute pressure. That is the pressure measured with respect to absolute zero, or basically with respect to the absolute zero vacuum. Okay, where the vacuum is also zero, that's the absolute zero. So the pressure measured with respect to that absolute zero, taking that absolute zero as a datum, that is known as the absolute pressure. And what is the gauge pressure? That is the pressure measured with respect to the gauge pressure. Please, this is pressure. Okay, pressure measured with respect to the gauge pressure, that with respect to the, no, oh, please make a correction. The pressure measured with respect to the atmospheric pressure. This is not the gauge pressure, this is the atmospheric pressure. If you take the datum as the atmospheric pressure, so the pressure that is measured using the datum as atmospheric pressure, that is known as a gauge pressure. Then what is the vacuum pressure? The pressure below the atmospheric pressure. Any pressure which is below the atmospheric pressure is known as the vacuum pressure. Then P absolute, C, this is the absolute zero or pressure or the complete vacuum, and this is a point A and this is a point B, and this is the atmospheric pressure. As you can see that this A point is above the atmospheric pressure, so this is basically a gauge pressure. This distance is the gauge pressure at P, and this is the negative gauge or the vacuum pressure. So if we need to calculate the absolute pressure at A and the absolute pressure at B, so that is absolute pressure at A is equal to atmospheric pressure plus P gauge at A, and the absolute pressure at B is equal to P atmospheric minus the negative gauge or the vacuum pressure at B. This is very important relations. You please always make a note of it, that the absolute pressure at A and absolute pressure at B, which is one is above the atmosphere and one is below the atmosphere, it can be calculated in the same way for any point which is specified in any problem or any question. Okay. Then we have the measurement of pressure. Now that was all about pressure. Now how to measure the pressure. The pressure measurement, there are basically two broad classifications of the devices, that is for the measurement of pressure. That is one classification is of the manometer and another one is of the mechanical gauges. What is the manometer? Manometer are basically a kind of device in which the in which the column of any fluid is balanced by the column of same or another fluid. Okay, and the balance of means a fluid whose pressure is to be measured, it is balanced by some another column. It can be of same fluid or it can be of different fluid. Basically it is kind of a balancing of two columns of fluid. That concept is used in manometer, and it is of two kinds. It is of simple manometer and it is a differential manometer. Simple manometer, you can take it as piezometer, you can take U-tube manometer, you can take single column manometer, and there is a differential manometer. It is a U-tube differential manometer and a simple U-tube manometer. What is the difference between this simple manometer and differential manometer? Simple manometer is that manometer in which we just measure the pressure at any one point. Means we are not concerned with 2 points, we are just concerned with 1 point, and the pressure of that 1 point is measured with respect to the atmosphere. Okay, so these are the simple manometers, and in the differential manometers we measure the pressure differences in terms of column of height or anything, height of any column or anything, means the difference between 2 points. So that is known as a differential manometer. And there is another devices that is known as mechanical gauges, that is the diaphragm pressure gauge, Bourdon tube pressure gauge, bellows pressure gauge, and deadweight pressure gauge. I will just suggest you to have a quick reading. These are basically not very much important from the exam point of view. You can just go and either you can just search for them about them in any standard textbook, or you can just look for them, you can just google these terms and you can just have an idea that how these what is the working principle of all these, because these are not very much important with respect to the competition point of view. And about these, the simple manometers and the differential manometers, I will go into detail in the coming slides. Okay, so let us start. What is a manometer? This is the definition of manometer. What are those? You can just write them, write it if you want. That these are the pressure measuring devices which are based upon the principle of balancing the column of fluid whose pressure is to be measured with another column of the same or different fluid. This is what I told you earlier. Then what is a simple manometer? It measures the pressure at a point in a fluid. Okay, at a point it is, and the differential manometer is, it measures the difference of pressure between 2 points in a pipe or in 2 different pipes. Then what is a piezometer? This is a kind of piezometer. This device is basically a kind of a piezometer. The one end is inserted at the wall of the pipe at the point at which the pressure is to be measured, and the other end is open freely to the atmosphere. Okay, and the liquid will form the free surface by which the magnitude of pressure is noted. If this is the height h, and you know that this is the liquid having the density of rho, so you can calculate the pressure at this point. A will be equal to rho into G into H. That is simple. And please make a note of 2 important statements here. The piezometer cannot be used for measuring pressure in a gases, as they do not form free surface, because the measurement using piezometer is simply based upon this height h, and if this height h is not defined properly, as in the case of gases, because they do not form a free liquid surface, so if this h is not properly defined, so you cannot get the magnitude of pressure. So please make a note that piezometer cannot be used for measuring pressure in gases, as they do not form the free liquid surface, and it is not generally used for measuring the high pressure in lighter liquids, because as you see, in the case of lighter liquids, the density will be very low. So this height will be very much high. As you can, I will just give you an example to completely understand this concept. See, we have just an atmospheric pressure. The same atmospheric pressure can be measured by just a 760 mm or 76 centimeter of mercury column, and the same, and for measuring same magnitude of atmospheric pressure, we need to have a 10.3 meter height of mercury height of water column. So see, you can just see, and if there is another liquid which is having a density much lesser than water, maybe in case of some oil or something like this, which is having a density is still lesser than that of water, so you can see that the height of that column, the liquid column, will increase further, more than 10.3 meter per 10.3 meter column, and you can see that 10.3 meter is in itself a very big height. So this makes the device, the length of the device, very infeasible to work with. So this is basically the concept that behind this statement is written, that it is not generally used for measuring high pressure in lighter liquids, because lighter liquids will have very less density, and if the pressure is high, if the pressure is less, so then you can use, but if the pressure is high, so that means that pressure is high, and if the density is less, so that means that value of the column, the liquid column, the height of the liquid column will be very much, and that makes the device very infeasible to use. Okay, and it has become very difficult to carry, and to, because you can itself note down that 10.3 meter of height of water column for measuring the atmospheric pressure is in itself a very big height, and you cannot take the readings and all those things. Okay, so that is why this piezometer is not used for measuring the high pressures in the lighter liquids. Okay, then you have another simple manometer that is known as a U-tube manometer. It is nothing but a U-tube. This is a U-tube that is a tube bent in the U shape, and the one end is connected to the point where the pressure is to be measured, and the another end is open to the atmosphere. Okay, you have some here you have some fluid which is having the specific gravity of S1, and this is your fluid, that is the manometric fluid, which is having the specific gravity of SM. See, these are the different height values which are shown here, that H1, H2, H3. Okay, this is the datum. So please make a note that I will always use this notation of HW, and I will always calculate the pressure at any point in terms of this column of water. Okay, I will always calculate everything in terms of the meters of water column, the height of water column, and I will also advise you to use this same concept, because by using this it becomes very simple to calculate the pressure at any point. Okay, so we consider that we have to calculate the pressure at point A, and if we consider that the pressure at point A be HW meters of water column, and we have seen in the earlier slides that we have a relation that H into S is a constant. Okay, so we will use this same concept, and from this point this we have HW, this is HW, and then we will go downward, and I have already told you that while going downward we have the increase in the pressure. So this is the addition H2 S1. If we reach this point, then and you always know that at the same height in the same fluid, please make a note, in the same fluid at the same height the pressure intensity is same. That is basically the hydrostatic law. Okay, so if the pressure at this point and pressure at this point will be same, so then we will go up to this is we are going upwards, so this will be minus, total height is minus H2 plus H1, this is H2 plus S1, and this is the then the specific gravity is Sm, and this is basically open to the atmosphere, so this is 0. And please make a note that these all the, if somebody asks you, the manometers generally we use whether we are calculating the gauge pressure or we are calculating the atmospheric pressure. See, you can already see here that we have taken, this is the open to the atmospheric, and we have taken here equal to 0. That means we are taking the data as atmospheric pressure, and the pressure I have already told you, the pressure which is measured which by taking the data as the atmospheric pressure, that is the gauge pressure. So the answer is simple. We calculate the gauge pressure in the calculation of in the terms of manometer, and if we use here some value for the atmospheric pressure, so then we can also calculate the absolute pressure. But in this case, when we are taking it as 0, atmospheric pressure is 0, that means the datum we have set as atmospheric pressure. So in this case we are calculating the gauge pressure. So on solving we will get the value of HW is equal to, in terms of this, and we know that pressure at any point is equal to rho of water into H of water into G. So pressure measurement of pressure will be very simple in this case if you take this HW, because you have to calculate this HW and then simply multiply it with water of density of water into G, that is the acceleration due to gravity. And please make a note of it, if you want to change this HW in terms of some other, if you do not want to take your you do not want to calculate your height in terms of water column, then you can convert it in some another in terms of some another fluid also. But please make a note of it, while calculating this pressure P, this density is also to be taken of that same fluid of which you have taken this H. Okay, if you have taken this as water, you have to multiply this with density of water. If you have taken this as alcohol, then you have to multiply it with density of alcohol. If you have taken this as density of any oil, then you have to multiply it with density of any oil. If you have taken it as in terms of height of mercury column, then you have to multiply this with the density of mercury. Please make a note of it that whatever be the fluid in terms of which you are calculating this H, the same fluid's density is to be multiplied for calculating the pressure P. This is simple, the U-tube manometer. And then another, the simple one is the single column manometer. What is it? It is in this also, it is a simple U-tube manometer. Only in this one limb of this U-tube manometer is fitted with a reservoir, and the cross section area of this reservoir is very much larger than the cross section of this tube. So this is the cross section of the reservoir is capital A and the tube is a small a, and in this case we have taken that capital A is very greater than small a. Okay, and from the conservation of mass we have this was the earlier level of fluid, and we have seen this when we have connected this, so the fluid the level of fluid in this reservoir has gone down by delta H. So we have that A into delta H, and because of that this water in this the fluid in this tube has raised by height H2, because when this A is not connected, this point is not when this manometer is free, means it is not connected to this point A, then the level of fluid will be same on both the sides. So when this is connected, because this is having some pressure, so when this is connected, this fluid has gone, the level of fluid in this reservoir has gone down by delta H, and it has raised by H2 in this tube. So we have from the conservation of mass, A into delta H is equal to A into H2, and then again we will take that in terms of water column of HW, and we will do the simple calculations as we have done in the earlier part. And we have this A by A, and this we can neglect because this A is very much greater than A, so this A by A can be neglected. So we have this term, okay. And if we see that if we are measuring the pressure of we can measure the pressure of air also, and if we are measuring the pressure of air in this, and the pressure of air, you know that it is approximately equal to atmospheric pressure. So you can just take it, that means that S1 is generally means approximately equal to 0 in case of gas. So if we are measuring the pressure of gas, then S1 is approximately equal to 0, and we will let HW is equal to H2 into SM. And again, for calculating the pressure P, we have rho water into H water into G. This is the similar concept, okay. And then we have this was the straight single column manometer. Then we have an inclined single column manometer, in which what we do, we have that single column manometer with one limb inclined at a certain angle with the horizontal. In this case we have inclined this limb with the angle of theta. Then similarly we have this A into delta H is equal to A into L. Please make a note of it that while applying the conservation of mass, you have to take this distance, okay. This length means A into delta H is equal to small a into capital L. And while calculating the pressure or while calculating the height of the water column, you have to take it in a vertical direction, okay, clearly vertical direction. That means if again you will do these things, the calculations, you will get it as L sine theta. And for measuring the pressure of gas, this S1 is approximately equal to 0, so HW is equal to L sine theta into SM. Or P, for calculating the pressure in terms of P, you will have rho W into HW into G, okay. And see, if we compare the expressions in the case of vertical and inclined single column manometer, we can see that L, because this HW, in this case you are using it L sine theta SM, and there it was H2 SM, so SM gets cancelled, and the L is equal to H2 by sine theta. That means that, and sine theta, you know, is always less than 1. The sine theta is always less than 1, because this is, and in this case it will lie between 0 and 1, because this is an acute angle. You cannot make this as an obtuse angle, okay. So in the first quadrant, the values of sine theta is between 0 to 1. That means that L will always be greater than H2. That means by inclining the single column manometer by any angle theta, which is between 0 and 90 degree, we are doing nothing but we are just increasing the sensitivity. Of the manometer. Means in that case, if H2 is very small, so that L will become somewhat greater than H2, and that it increases the sensitivity of the single column manometer, okay. This is just the advantage what we are getting in the case of inclined single column manometer, that we are just increasing the sensitivity, or we are just increasing this height L, okay. Then we have YouTube differential manometer. See, in the differential manometer, it is nothing but we are just measuring the difference of the pressure between this point A and this point B. Similarly, you can see all these heights. You can see you can have a single manometric fluid also, you can have a double manometric fluid also. We have used a double manometric fluid also, which is having a specific gravity of S3 and S4. So, and if you will, this is HAW is the pressure in terms of meters of water column at A, and this is at meters of water column at B. And if we do all these calculations, you can see that HAW minus HBW is equal to this term, and this HAW minus HBW, you can write this as simply as HW, okay. You can just take it as HW, and P in terms, you can write that P rho W into HW into G. This is the pressure difference in terms of meters of water column, in the height in terms of height of water column, and this is in the terms of Pascal or kilopascal, whatever be the suitable units you find. This is the YouTube differential manometer. And then you have another, that is the inverted YouTube differential manometer. See, another simple thing, the same thing is to be done in the case of the differential YouTube manometer also. You will get this HAW minus HBW is equal to, in terms of this, you can just try these expressions, finding these expressions yourself. These are very easy to get. You can just follow the steps, just follow the hydrostatic law, that while going up the pressure decreases, while going down the pressure increases, and at the same level at the same horizontal level in the same fluid, the pressure intensity is same. Just use these concepts and you will easily arrive at these expressions, and this again can be written as HW and P is equal to rho W into HW into G. And please make a note of one thing, that if you are asked somewhere that where we used inverted U-tube manometer and where we used a inverted U-tube differential and where we use a simple U-tube differential. Okay, the inverted U-tube differential we use in that place in which these fluids are heavier than the case of than this manometric fluid. If these fluids at A and B are very much heavier as compared to this manometric fluid, so we use that inverted differential manometer. And when these fluids at A and B are lighter as compared to this manometric fluid, so then we use the U-tube differential, simply U-tube differential manometer. And in this case you can also see that this is S3 and this is S4, so you can clearly make out that the specific gravity of this manometric fluid 1 will always be less than this specific gravity of this manometric fluid 2, otherwise this fluid will mix into this. Okay, so this should not happen, this should be two immiscible fluids. Okay, and means that there is a simple that U-tube differential is used when these fluids whose pressures to be measured are lighter than the manometric fluids, and the inverted U-tube differential is used when in the case of when these fluids to be measured are heavier than this manometric fluid. Okay, so that's all for this lecture. Thank you for watching this lecture and have a good day.